All right, now we're going to do something very groundbreaking. Up until now, the algebraic structure that we've been talking about is the idea of a group. A group is a set with an operation that satisfies certain properties, inverse, associative, and so on. We're going to introduce our second algebraic object called a ring. Polynomials are a primary example of this type of algebraic object. We've already noted that polynomials have two operations, plus and times, which kind of sets them apart from the group. So let's run with that and see where we get. All right, first of all, let's define our summation notation for polynomials. We've seen similar summations in the Summation Notations chapter. These a's are the coefficient, that is, ai is the coefficient of xi. The leading coefficient is the coefficient of x to the n, and n is called the degree of this polynomial. Okay. So some exercises to reinforce this idea. And here we define a polynomial ring. So a set of polynomials is called a polynomial ring if two operations, which we'll call plus and dot, are defined on the set of coefficients. Now this does not have to be regular plus and dot. It's just some operation that's called an additive operation and some operation that's called a multiplicative operation. Now these two operations have to satisfy the following conditions. The coefficients form an abelian group under plus, which as usual has identity element 0. The non-zero coefficients form an abelian group under dot, and the identity element is denoted as 1. And the operations plus and dot on the coefficients satisfy the distributive property. Okay, so these are conditions on the coefficients of the polynomials. We still use the regular plus sign to add the terms together. Actually, if you think about it, in polynomials, the various terms remain very separate. Only when you multiply, two terms may become a term of a different degree, but in some ways, the terms are very separate. Some remarks here that are important. Most other references don't have quite a restrictive definition as this, but this is good for our purposes. All right, so, and in the future when we talk about polynomials, we'll be presuming that the polynomials are in a polynomial ring. There are polynomials that are not polynomial rings. Okay, and that we'd explore that in this exercise. In particular, if the coefficients don't form an abelian group, then you don't have a polynomial ring. So we explore that here. All right, now let's define some other notions about polynomials. Two polynomials are equal if and only if all their coefficients are equal. All right, so they have to equal in every term. And if they equal in every term, they're considered as equal polynomials. Now we define in a formal way what the sum of two polynomials is. And what we're basically doing is we're adding the coefficients of like terms together. Now notice here this max m and n, this summation may not go up quite as far as this one, but you have to make sure to include the highest order term. So max m and n will be the largest of the two degrees. And if there's no explicit specification of the coefficient, we just assume that it's 0. This is just a formula that exemplifies what we typically do when we add polynomials. Now it turns out that polynomial addition is commutative, which shouldn't be a surprise because the operation on the coefficients is presumed to be commutative. And it's also associative, and you can prove that similarly. And polynomials under addition have an identity and an inverse, so you can explore that. Okay? So we've actually shown all the properties of groups. So polynomials under addition form a group, and it's also abelian if the coefficients are abelian. Now what about multiplying? We saw previously when we multiplied two monomials together, for instance 4x squared and 8x cubed, the power of x that resulted was x to the fifth. How did the 5 come from? 2 plus 3. Okay? So it stands to reason that if p of x is a polynomial of degree m and q of x is a polynomial of degree n, the degree of the product is going to be m plus n, because the largest power in p is m, largest power in q is n, so the largest power in the product should be m plus n. Okay? So we know that the product of two polynomials will have this form, but we need some expression for the coefficients. Right, so let's see what we can do with that. Right? Well, suppose we express p in summation notation, q in summation notation. Here we are using the distributive law. It's a little bit bogus because we're actually going to use the special operation plus on the coefficients and the regular plus sign to join terms together. But if you notice, if we group these together, every term is going to look like this. There's going to be an AI and a BJ, and the power of x is going to take I from the A term and the j from the B term. So we can rewrite this expression in the following way. All right? So let's go power by power. Consider terms of this form. What are the terms of this form that multiply x to the 0? Well, the only way to have x to the 0 is if I is 0 and j is 0. So the x to the 0 term must be a0, b0. Let's think about 1. Suppose we have x to the 1. Two possibilities. Either I equals 0, j equals 1, or I equals 1, j equals 0. Those are the two possibilities here. Okay, so this gives us our coefficient for C1. We can do C2 similarly to get x squared, where 2 is I plus j. We could have 2 and 0, 1 and 1, or 0 and 2. So if you look at these three, you begin to see a pattern. Okay. So, and the pattern is here. You start with a0bk, that means that b has the largest possible degree and a has the smallest, and you go all the way up until a has the largest degree and b has the smallest. Now, if you don't quite see the pattern, do some examples yourself and see that this actually works out. Now if I write this in summation notation, let's consider the subscript on the a. It goes from 0 up to k. So I'm going to let I be the index that gives the subscript on the a. I equals 0 to k. What is the corresponding subscript on the b? Well, if I have ai, then a little thought should convince you that the subscript on the b will be k minus I. Why is that? Because the sum of the two subscripts has to be k. Right? So that's how we get this formula, which is a general formula for the coefficient of the product. So we're going to define the product of two polynomials in this way. And again, this actually is you're using the coefficient operations. If you're just using real numbers or integers and so on, you don't really have to worry about that. But here's another example. All right, and here's some other practical examples. So you can look at those. And here's some that you can try for yourself. All right, you can do multiplicative identity of the polynomials. And then here you investigate the situation of multiplicative inverse. You have an exercise to look at the associativity under multiplication. It's kind of a long proof. But the upshot is that, in fact, multiplication is associative. And we'll stop there.